This video covers frequency and phase modulation, presented by Dr. V. Santosh Kumar.
We will explore the history of FM and why it is used to solve noise issues in linear modulation systems like AM, SSB, and DSB. We will also cover key definitions such as deviation, Wideband FM, WBFM, and Narrowband FM, NBFM, and note that FM is very popular for VHF voice applications. The FM signal for a baseband signal XT is defined by a mathematical equation. Here, Kf is the frequency deviation constant in Hertz per volt. An FM signal is a constant envelope signal with varying frequency or phase. The instantaneous frequency and maximum frequency deviation are also given by their respective equations. Observing the FM signal in the time domain, we see a baseband signal as a pulse train. The corresponding FM signal shows frequency variations that mimic the pulse train amplitude. For a sinusoidal baseband signal, the FM signal in the time domain exhibits continuous frequency variation, higher where the baseband signal amplitude is higher, and lower where the baseband signal amplitude is lower. In the frequency domain, for a 1 kHz sinusoidal baseband signal and a 10 kHz carrier, the spectrum shows sidebands spaced by 1 kHz. The FM signal spectrum is wider than AM or DSB signals. The instantaneous frequency and frequency deviation are key concepts. Maximum frequency deviation is delta F. The deviation ratio D is delta F over the bandwidth W. The modulation index B is dF over FM. These ratios define narrowband FM when B is much less than 1, and wideband FM when B is much greater than 1. Bandwidth is approximately 2 times the sum of D and 1 times W. The FM spectrum plotted against the modulation index beta shows a typical trapezoidal shape in linear frequency and amplitude in decibels. The deviation is 2 times the maximum deviation, and the carrier is in the center. This graph illustrates FM modulation with a carrier frequency of 1 MHz and a modulation index beta of 2.5 using an FM of 2 kHz. Here we see FM modulation with a higher modulation index, beta equals 10, and the same carrier, an FM. This final spectral plot shows a very high modulation index, beta equals 100, which results in a much wider and denser spectrum. Comparing FM with AM, DSB, and SSB, FM typically has the widest bandwidth. The signal-to-noise ratio for FM is nonlinear, unlike the others. FM efficiency can be up to 100%, and its complexity is generally considered high. The threshold effect shows the trade-off between carrier-to-noise ratio and recovered signal-to-noise ratio for FM and AM. A key advantage of FM is the capture effect, where signals more than 6 decibels down in power will not interfere with the stronger signal. This block diagram outlines the structure of an SDR program for narrowband FM. It includes a GUI for interaction, a transmit path to the USRP, and a receive path from the USRP. This shows the detail of the transmit path, which is always running. It includes blocks for audio source, audio gain, resampler, FM modulator, and transmit gain, sending 320 kilo-Siemens per second to the USRP. The receive path is also always running. The signal flows from the USRP at 256 kilo-Siemens per second through a low-pass filter, the FM demodulator, and squelch. From squelch, the signal goes through audio gain, resampler, and finally to the audio sync. Now, let's define a PM signal. For a baseband signal XT, the PM signal has a mathematical form where Kp is the frequency deviation constant in radians per volt. A PM signal is a constant envelope signal with varying frequency or phase. For a pulse train baseband signal, the PM signal in the time domain reflects the pulse train's amplitude as phase changes. For a sinusoidal baseband signal, the PM signal's phase changes continuously, mirroring the amplitude of the baseband sine wave. In the frequency domain, for a 1 kHz sinusoidal baseband signal and a 10 kHz carrier, the PM signal spectrum is shown. Similar to FM, the spectrum is wider than for AM or DSB signals. Finally, comparing the bandwidth for FM and PM, the bandwidth is given by the approximation 2 times the sum of the deviation ratio and 1, multiplied by the message bandwidth W. Increasing frequency has a more profound effect on the bandwidth of PM.